All right, welcome everyone to CCOM seminar. Today we have Dylan Mikesell talking. He's currently at MIT, but Dylan did his bachelor's in geophysical engineering at Colorado School of Mines. He worked on his PhD in geophysics at Boise State University. Between his degrees, Dylan did some work as a geophysical project engineer in non-destructive testing at Olsen Engineering. He then did a postdoc in France, and he's now a postdoc as an NSF fellow in the Earth Resources Laboratory at MIT. And he's going to be talking about seismic interferometry today.
Okay. Hello, everybody. Thanks, Josh. As he said, I'm going to talk about seismic interferometry. I thought I would first see by a show of hands who is familiar with this term. Okay, just what I thought. So like Josh said, I'm a seismologist, but I think with what happens here with seafloor mapping and hydrographic mapping, there's a lot of overlapping techniques just because we're still dealing with seismic waves, you're dealing with acoustic waves. The processing is a lot the same, sometimes it has a different name. But I'm going to talk today about seismic interferometry, which is a new sort of field in the last 10 years that's designed to utilize the seismic noise that you would observe in the background of the Earth. So earthquakes are how we get our sources for imaging deep into the Earth. If we want to image shallow, we use big shaker trucks in an oil exploration type setting, or we use a sledgehammer if we're interested in, say, the water table. But we can do a lot with just the seismic noise that's constantly in the background, not related to any of those things. And I want to start with a little bit of motivation as for why this technique came up. And the first thing is we can think about imaging advances. So in 1970, you would get a CAT scan of your brain where you have resolution, pixel size, about 3 millimeters. Fast forward to 30 years later in 2001, you're at 6 times the spatial resolution, so half a millimeter, and you sped up your acquisition time by an order of magnitude. And we have the same sort of thing going on in seismology, where we have more instruments, we have faster computers, we can record more data, but you haven't seen the same sort of big scale improvement where you go from a super blurry image like this to a really high resolution image like this. And there's a reason for that, and it has to do with our resolution in seismic imaging being constricted by our illumination. So if you're on a boat in the ocean, you're scanning along, you have a source and a receiver everywhere, or at least at the surface that pings down. In seismology, we don't. And one way to visualize how that affects your image is just looking at this picture. So if you illuminate this woman from one side, you can tell that she's holding a banana. You can tell that she has 2 legs. But if you go and illuminate her from the other side, you can't see the banana at all. It looks like she has 1 leg, and now she's holding a pineapple. And this, if you're limited in where you can illuminate the subsurface or record data, you're limited in the resolution of your image. And so for CAT scans, they're really lucky. They can just go around the whole brain, 360 degrees. And not only can they do that, they can change which source receiver pairs they use, so they can get different directions of incidence and reflection. And then, just like seismology, just like hydrography, you record some data, stick it into a computer, and out pops your image. But in the Earth, our images don't look so great. And it's because of this resolution thing. So this is a geologic cross-section. If you look at it, you say, oh, there's a lot going on. But if you look in closer detail, you see all these little question marks. And this is because we still, even though we have sources and receivers, say, at the surface and maybe even subsurface sources, our illumination is not great enough that we can resolve everything. And in particular, in earth sciences and seismology, we can't resolve things that have steep dips, like faults. we can't resolve layers that are too thin. So our resolution in the vertical direction is a function of our frequency. The Earth acts as a really nasty high filter frequency. So in the water column, you don't have this so much, but in the Earth, you have a lot of energy converted to heat. So the signal in the high frequencies is attenuated and doesn't penetrate very deep. I meant to say, feel free to ask questions if you guys have any. And so if we come back to this idea of the Earth and look at where we actually do have sources and receivers, you get these two pictures. So if we want to do deep imaging of the Earth, you're limited to earthquakes, which mostly occur at the plate boundaries. Most of them also occur very shallow. So the yellow dots are within the top 70 kilometers. And in a few places, you get deeper earthquakes. And so you're spatially limited with your sources. And if you look then to your receivers, you're also spatially limited with your receivers. Most of them are on continents. Most of them are also on continents that have more money than others. But we're never going to have the capability to use natural sources and our receivers and try to get really high resolution images of the subsurface. And so in the last 10 years, there's sort of been a revolution with this technique, seismic interferometry, where we no longer need these types of sources to do imaging in the upper crust. And so I'll introduce now seismic interferometry. And I'll get more into this, but the basic idea is that if you have some sort of source, it can be noise, it can be an earthquake, whatever, and two receivers that record some time series, if you cross-correlate the two, you get information about the travel time between the two. So that tells you about the velocity between those two receivers. And so this idea of seismic interferometry is just that you record some data, you cross-correlate it, and in the end, you create what we call a virtual source. So now x prime is what your source is. And I'll show you a real data example. If we record some noise, so this is seismic noise, we do a little bit of processing to it. If you notice, the main thing is we just normalize the amplitudes. So a sliding window, we get rid of these big spikes and everything looks like it has the same amplitude. We cross-correlate that noise, and then we do that for, say, multiple windows of 600 seconds, and we stack them together. You get something that looks like this. So I don't know how you guys visualize your data in hydrography, but usually we do it as a function of offset across the x-axis and time on the vertical axis. And what you see here is a very coherent signal that has some sort of move out. And that move out is related to the distance between each of these traces, or each of these stations, and the station that we cross-correlated it with, which is not shown here, and the velocity between the two. And so the idea is you can just take all this noise, cross-correlate it, and boom, out pops some signals. And in this particular case, it's surface wave signals. So I don't know how many people are familiar with the different types of waves that we get in seismology, but we have surface waves, we have P waves, we have S waves, and that's because we're dealing with waves in elastic media instead of acoustic. And if you look at some of the characteristics of this wave, in particular the dispersion characteristics, you can say something about the subsurface. So surface waves, when I say dispersion, I mean that the different frequencies travel with different velocities. And you can measure the different times that it takes for the different frequencies and then invert for what the velocity structure is. And if you're wondering, well, why the hell does that work? Why can you just take noise, cross-correlate it, and get a signal? It's pretty interesting, and there's been a lot of work recently looking at what generates the noise. And I thought I would put this slide with some information about where the noise comes from, because you guys all deal with the ocean. And I don't know so much about this stuff, but I know enough that I can explain it. So in the top, you see a little GIF image that's showing a very monochromatic wave, the red wave, propagating from left to right, and the black wave coming the other way. And these are actually modeling of ocean gravity waves. So just the swell that you have of waves propagating through the ocean. And what you notice is when the black and the red line up in phase, you get the big blue. So the blue is the sum. And you see that you have a propagating wave with big amplitude in the blue, which is coming from the interference pattern. And if you were to just take a bunch of noise, record it at a seismometer almost anywhere in the world, and look at the power spectral density to see where the energy is in the different frequency bands, you see this huge spike here, around 5 to 10 second period. So 0.1 hertz. And what that is what's called the secondary microseism, which are these ocean standing waves. And what you have is a big ocean wave at the surface that comes, is created, and then actually propagates as a pressure wave down into the crust and is coupled into the crust as a seismic wave. And that happens all over the Earth, and that's the signal that when you cross-correlate, noise comes out to tell you something about the coherent signal in that image on the right. And so we can look at what causes that, or where in the world you would expect to get this kind of noise. The image on the top comes from the group in Paris and the group in Brest, where they do a lot of this, these simulations. But you have the bathymetry, so you guys, I'm sure, are very familiar with those maps. And then you have what they call... I'm sure you do. I'm sure. Then what you have here on these two lower maps are what's considered the amplification factor. And so you have these two standing waves coming together that create this one big wave. And depending on how deep the seafloor is relative to the frequency or the wavelength of that standing wave, you have energy that gets coupled into the ground very well. So here is the map showing for 6 seconds. Yep.
I need to clarify something, to understand something better. So you're not talking about energy induced by surface ocean waves. It's really the standing wave is what's inducing the ocean micro.
Yes.
So it's a resonant wave that's at some period that's scaled to the size of the ocean.
Scaled to the depth.
The depth.
Yeah, exactly.
Yeah.
And so you see here areas where you have a big amplification factor. That's where you're at the right depth that you hit that resonance, and it just sits here and goes like this constantly. And if you go to a little bit longer period, so longer wavelength, you get more sensitivity out a little bit deeper in the ocean. And so at the same time that we've been working in seismology to analyze the noise, there's a number of people that are working on figuring out modeling of how this noise comes about. And there's some really interesting features. So if you look at it as a function of time, so here is noise for January, I think in 2008, yeah? You see most of the energy is coming from the northern hemisphere where you have big waves due to winter storms. In August, you have the opposite. You have all the winter storms in the southern hemisphere that create these big waves and make a lot of energy. And then if you look overall at the year, you see it's pretty well spread out to the north and south, I would say mid-latitudes. And then there's also energy that comes from waves reflecting off the coast. But that's actually a small component of the overall ambient noise field in the seismic part.
What about the breaking waves?
Yeah, so
is that the breaking waves?
Yeah, these I think are the breaking waves that come in. And
that should cause a lot of racket.
I think that they do, but I don't know that the amplitude, I don't know if it's the same as these big standing waves. Okay, so that brings us back to this idea. If you have, say, ocean waves that are coming from here, you can just cross-correlate the two and turn one of them into a source. And it's actually a little bit more complicated than that, as the story goes. So I'm going to sort of show you the assumptions that go into this. And if we satisfy those assumptions, we can do some really cool stuff as far as seismic imaging goes. So this is what we want to create. We want to create a virtual source. I'm just going to show you an acoustic homogeneous velocity model. But what we take is a source, we shoot it off, we record it at each of these stations, and we cross-correlate that time series. What you get here on the right is the cross-correlation. And if we move that source to somewhere else, you see that these red arrows are almost the same length, So that means that the arrival time at the two stations is the same. When you cross-correlate, you get something that comes in around 0. And if you do this for sources all the way around on this surface, you get this function here. So it's the cross-correlation as a function of source number, where I have a source every half degree. And I'm going to change this now to a grayscale image and sum it. So I sum over all the sources, and what do you get? A really nice single peak arrival. And that's actually, if you take the positive time, it's the virtual source as if it was at x prime. And if you take the negative time, it's just the reverse. So it's if you had a virtual source at x. And I'm going to show you, if you're confused about why you would have a positive and a negative time, I'm going to show you this video, also related to studies. So this is a pool. They just threw a washer in, and then all the way along here are transceivers or hydrophones maybe, and they're just going to record the wave field that propagates out. And they record it on a complete surface all the way around. And then what they're going to do is take that time series, flip it around, and play it back in. So they start where they ended, and they play it backwards. And if you watch, you see all this scattered waves that have been sort of reflecting around the boundaries. But eventually, something forms that looks like a coherent wavefront. Eventually. Here we go. So it goes back, it collapses on itself, and then it reemerges like there was a real source there. So this would be the positive time in that cross-correlation function that we saw, and before that it would be negative time. So it collapses exactly where the source is. And there's been a whole lot of research in something called time reversal, and they use that for all kinds of different things, from medical imaging to material characterization. In medical imaging, they want to be able to focus ultrasound somewhere in the body to break up, say, calcite. They do time reversal stuff like this to focus a bunch of energy there. Okay, so in the real Earth, we have our theory now. We just record a bunch of noise, we cross-correlate it, and out pops some data. I want to go into showing you now what people do with this kind of data. So if you're not familiar, in the US right now, we have what's called the US array, which are 3-component seismometers, high-rate GPS, as well as magnetotelluric stations that are moving across the US from west to east, with approximately 70-kilometer station spacing between them. And this is just an example from the very first set, where we had mostly covering the western US. We take a bunch of noise for a year, and we cross-correlate this station with all these other stations. And if we plot just the positive time, you get this, which is a really nice surface wave propagating through the whole crust. And it has actually, if you're familiar with what dispersion looks like, you see that this waveform is stretched out. That's due to the dispersion. And if you plot this then as a function of amplitude at each of these stations with time, so this is at 100 seconds, and this is at 200 seconds, you actually see that you've created a virtual source with a wave propagating away. So it's pretty cool that it just works. And if you look at it, you might be critical and say, okay, what's happening right here? Why is there no energy? Why is there no energy? And we'll talk about that once we get through these examples. But if you do regular tomography, so you measure the time that it takes for a wave to go from one station to the other station for all those different station pairs, and then you invert for the velocity model, you get something that looks like this from noise, and if you do the more traditional one where we sat around and waited for earthquakes, you get something like this on the right. And you can see they're almost identical. So what does that mean? It means that we don't need earthquakes anymore. We can just go out, put out our seismometer, record data for a year. It could be noise, whatever. We do some very simple processing, we cross-correlate it, and then you could start doing geologic or seismic mapping of the whole crust. Beyond that, people have said that you can even go look at the anisotropy in the crust. So when I say anisotropy for seismic waves, I mean that waves have one speed in a given direction and another speed in the other direction. And usually that tells you something about either the fractures that are within the rock, the local stress. In the crust, it actually tells you if you have a asthenosphere moving under the lithosphere. So if you look at the wave velocity, so on the y-axis here, as a function of azimuth from this source, so you take all the stations that fall within 15 degrees, and you look at how long it takes for a wave to go from here to there, and then you move to the next 15 degrees and sum those all up and look at the average, you get each of these little red dots with the standard deviation on it. And if you fit the green curve to it, you can pull out the anisotropy parameters, which tells you about the wave speed in the different directions. And you see that these are at different periods, so 12 seconds, that's sort of the upper crust, 26 seconds, lower crust, and 38 seconds, you're getting into the asthenosphere. You see very big changes in wave velocity as a function of direction. And you see differences at different parts of the US. So here the peak is maybe at 60 degrees, and here the peak is at 150. So it's telling you something about how the asthenosphere is flowing underneath the lithosphere. And what people are interested in is what's happening underneath the US. So you have the plates converging, you have some strange rotation up in the Seattle area, and then you have the basin and range area here. And this can give you some insights into that. But I would be skeptical if I was to look at these and say, oh, you can just do that with noise. So if you think back to that image where we showed all the sources on the surface around, they all had the same amplitude, they were evenly distributed, and when you sum them up, you got a really nice impulse response between the two sensors. In the real world, we don't have sources, even the noise sources, that are evenly distributed and even the same amplitude. So if you're close to the coast and you have lots of waves crashing, that's going to be different in amplitude of the noise versus if you're further inland. And so some current work that we're working on right now is how do we try to make sure that we're not interpreting, say, this kind of fluctuation when it's actually due to the noise sources.
So how do you know that this are crustal velocities? Because their phase velocities are different than the speed of sound through a granite or through a metamorphic rock.
Yeah,
Right?
so these are from surface waves. And
Oh,
so
just from surface waves.
These are just surface waves.
Okay.
And surface waves have a sensitivity with depth.
Yeah.
So longer
Because they're Rayleigh
period,
waves,
sample
basically.
deeper. Exactly,
Yeah.
they're Rayleigh waves. So these longer periods, by definition, sample deeper into
Yeah,
the
that's why the
crust.
slow velocities.
And this is just an example where someone did a numerical experiment. The true velocity is the dotted black line. The black velocity is what they get if they do some numerical simulations, but they alter the source amplitude around this circle. And you see that you have overestimation, you have underestimation. If you were to take the average of the black line, you get this, which is off by maybe 0.5%. If you tried, you could actually fit this 2 theta sine curve that tells you about the anisotropy, and that's this line here. And that actually looks like significant anisotropy that you would then want to interpret in geologic terms as some flow or some preferred fracture orientation, but it's purely due to the fact that you don't have noise sources surrounding your 2 receivers that have even amplitudes. And we can think about this if we come back to our very simple model and analyze which part of this source circle contributes to our actual response. And what you notice is it's only this part here where you have the maximum or the minimum in this function that when you sum constructively. Everything else sums destructively. So we call these the stationary phase sources. And if you want to get an idea of what it actually means, it's when there's a source that's directly in line with these two receivers. So I indicate that by that red box. And then on the opposite side, you have a source going in the opposite direction. I guess I could use this. And if you cut out all the stuff in the middle and you still sum it together, you get almost identically the actual impulse response that you had if you had the whole surface. But what you also get, if you look at these areas where you're in the non-stationary phase zone, if you sum those, you get something that looks like an actual wave, but it comes in too early. So you can have an apparent velocity that's too fast purely because of the energy distribution of these sources surrounding your receivers. And so this is something that in the field of interferometry is sort of where we're at with trying to improve upon the method. So we have a very good idea of how it all works, and we want to figure out how we can ensure that we're not actually measuring apparent velocities because of the source distribution. And we call these artifacts. Yeah, I don't know what I was going to say with this slide, but this is what happens. You see that you have, here is too fast, and that's because you have this advance when you don't have sources in the right place. So the next thing we could ask, well, is how can we get rid of these artifacts? And we can do some very interesting signal processing stuff. The basic of what I want to show now is something that we call multidimensional deconvolution. I'll try not to get too boring and heavy like this. It's a big word, but it's a really easy idea. So you have your two receivers, and you have your receiver. You have your two receivers, and you have your sources everywhere. But in the case that you only have sources in these shaded gray areas, you can actually correct what this impulse response would be if you had an extra array on this side in between where your sources were and the receiver that you were trying to correlate with. And what happens is, for all these different amplitude sources, the energy all goes through here, you record it, and so you know the imprint that it leaves on this receiver. And so we can do that with some real data. So this is off the coast of Canada, north of Vancouver. And we have one array here, and we have another array here, and we're going to take this array and we're going to try to make this station here a virtual source. And if you look at the geometry of the array, you have a lot of energy coming from this direction where things would create artifacts, and you have a little bit of energy coming from this direction. And so the first thing that we have to do is choose which sections of that noise we want to use. And we do that by beamforming. And I think you guys use beamforming in a very different sense than what I use it for. So what I use it for is I take an array and I just look at which direction and with which velocity the energy arrives at the array. And then I project it back into the subsurface and plot it as a function of azimuth and as a function of what we call Rayleigh parameter, so the inverse of velocity. And for Rayleigh waves, you have something in here that's around 0.3 for the Rayleigh parameter. And what we did is we just tried to filter through all the noise, do beamforming on 10-minute windows, and pull out any of the sections where you have energy in this upper quadrant. And if you cross-correlate, say, this receiver with all the other receivers, you get something that looks like this. So you have a spike here at 0, so this is the virtual source, and then you have energy that's spread out along the other receivers. And in the ideal world, you would want to have this for your virtual source, which is just a spike at that one receiver, like its real source. And when you have this uneven distribution, it gets smeared out like this. So what we do is we record this on this array here, and then we deconvolve that from this receiver signal. And in the end, what you get, so the black line is the new data, and the red line is the old data. And you see here, you suppress all these different artifacts that would come in. And so this is sort of where state-of-the-art, what can we do signal processing-wise to continue to improve the signal that we get from noise. And if you look at all the stations from that southern receiver array, you actually see some pretty considerable differences if you're talking about analyzing 1 to 3% velocity changes because you want to say something about the anisotropy in the subsurface. And you can see directly right here, we look at the phase velocity as a function of frequency. For the very basic cross-correlation method where you don't do anything to the data, you just sort of record it, play with the amplitudes, and then cross-correlate it, you get these two red and green curves. And so you're seeing directly the dispersion here. So each velocity has a different frequency. If you go to the more advanced cross-correlation technique, where you do some spectral whitening, so you mess with the frequency spectrum of the data before you cross-correlate it to try and balance out the energy in the different frequencies, you get this blue curve. And then if you do multidimensional deconvolution, you get the purple curve. And what do you know? None of them match. So, what can we say? Is the state-of-the-art cross-correlation method where you do spectral whitening any better than the multidimensional deconvolution? I think that the jury is still out. But that's what we're investigating. You see that for sure, if you just cross-correlate the signals without doing anything, you get crazy-looking velocity profiles that actually make no real sense. So we know that that's wrong. And as far as what's happening now, we can start to implement this kind of stuff on a big scale across the entire US. So this is back to the picture that I showed earlier with the US array. It is actually now in Alaska starting in 2014. So we will have everywhere except Hawaii, I don't think it's on this map, covered. And each station actually occupies its location for 2 years, which is plenty of noise recording that we can do this kind of stuff. And that's where you're going to see, in my opinion, a lot of interesting observations and discoveries made in the field of seismology in the coming years. Now this data is all available, and I don't know if there's any seismologists here. They're probably familiar. It's through EarthScope and IRIS, and like this data is open to everybody through IRIS as an internet data archive system. Okay, and so the conclusions of this, my overall goal that I hope you guys take away from this is that Earth's ambient noise contains useful information. So for the last 50 years, we've looked at this, say, secondary microseism peak that you see in the power of spectral density, and people just want to kill that and get rid of it. That's not the case anymore. The ambient field is mostly generated by ocean microseism. And these correlations can be used for all kinds of different things, from tomographic imaging to monitoring changes in velocity through time. So that's something that people are also working on. If you can have this station out here for 2 years recording noise, you can almost create one of these impulse responds stably on a monthly basis. So then if you have a stable estimate of the impulse response every month, you can start to look for changes over time. And there's some really interesting work that people have shown in Alaska and the Cascades. Just the local snowpack annually, that weight of the water changes the velocity by compressing the sediment and the material of the crust, that you can see differences in these noise correlation functions. So there's a lot of cool things that people are going to start doing with this. There's a couple people that have contributed to this work. And just to come back to wrap up, how I said you're seeing this in the US because we have this nice station density. You're also seeing it in Europe. So this is an example where people are taking all the passive sensors that you have. Pretty soon there's a whole Eber array that's all over the peninsula of Spain. And you're going to be able to start mapping large-scale crustal features. And in this particular example, they point out that they see these low-velocity basins where they're filled with a lot of sediment, these massifs where you have batholith intrusions that are high velocity. You see in Canada, so if you look at the US station density versus Canada, it's orders of magnitude better in the US, but just by having these here, we can cross-correlate every single one of these stations with everything in Canada and get one of these impulse response between the two that tells us something about that material. And so you see some really interesting stuff, the Canadian Craton, Yellowstone hotspots, all kinds of stuff. And I'm going to end with this. So all I showed so far is surface waves, but there is definitely emerging work, so since 2012, where people are recovering body waves. And in this case, this is an earthquake record compared to a noise correlation record. And what right away you notice is now you have this huge density of stations. That's because these were at different times. But you can see MOHO reflected S waves. You can see multiply reflected MOHO S waves. And then you see down here your strong surface wave. So in the future, we're actually then also going to be able to not just do sort of this surface wave imaging, we're going to be able to do reflection imaging of the bottom of the crust, the mantle discontinuity zones, core mantle boundary, all kinds of different things just from seismic noise. So that's the talk. Yeah.
How does the bandwidth of a noise-induced source compare to the bandwidth of a typical earthquake source?
Good question. The bandwidth of the noise is very small compared to an earthquake. So you actually see for the surface wave stuff, we're sort of stuck in this 1 to say 15-second period range. And so that's limiting in how shallow we can resolve as well as how deep we can resolve. There's other work now where people are taking, so you have a big earthquake, the main wave comes through, but that main wave excites all kinds of multiply scattered waves that then sit around and resonate, especially in basins that they call the coda waves. And you can actually, instead of doing cross correlations of the noise, do cross correlations of the earthquake coda and get signals from 50 seconds up to say 2 hertz, so half a second. And that, so if you think about utilizing the earthquake coda waves in this sense that they're noise and you just cross correlate them, you can get a pretty broad bandwidth from that. But for the microseism noise, you're stuck sort of in this peak that I showed in the power spectral density plot.
And I should mention for our students who are acousticians, or want to be acousticians, that there is an equivalent, well, it's not really equivalent, but there are folks who try to take advantage of ambient noise in the ocean too.
For sure.
Look at signals.
So Bill Cooperman,
Yeah.
he had a couple postdocs in the early 2000s that sort of straddled the line between earthquake seismologists and marine seismologists, and they did a lot of the work. So a lot of this is taken actually from acoustics, for sure. Yep.
So it looks like the technique may have some limits once you get off the continents where you are unable to put up receivers, or
Yeah, so exactly. It only works where you have, let me go back. It only works where you have receivers. So the fact that you have the noise created sort of everywhere, it still is only useful if you have 2 receivers somewhere. So a big problem is still here with your receiver distribution. We can only say so much about Earth's crust in the continents and not so much in the oceans, just because we don't have any data there. But the noise is still there. So there's some new experiments around New Zealand where they put a bunch of OBS on this shallow side of New Zealand and record this seismic noise for a year and a half. And lo and behold, that signal's still there. They can do all kinds of nice tomography, get an idea of the upper crustal structure if you have the data. for sure.
The Japanese have 1,000 wired OBSs offshore.
Yeah, so, yeah, going off this way, yeah.
1,000.
Yep,
Amazing.
so if you can get the Japanese data if you can type in Japanese.
Well, presumably the ocean observatories also have OBSs, stationary
I would think
OBSs
so,
that are
yeah.
wired to land,
Yeah.
because there's several of those going in now.
Hopefully those people know about this stuff.
Yeah, I hope so.
If you have an ocean basin like the Arctic that's surrounded by continents fairly closely, do you get some advantage there? I mean, in your,
As far as generating the noise,
or recovering the noise, and, you know, in this projection, the Arctic's stretched all
stretched
across
here,
that way.
yeah.
How much, if it's ice covered, you're not going to generate.
I mean, you have to have the wave first of all. So, I mean, I don't know, you guys would be the pros. The sea ice comes down to here in January, so that at least you have some of these big storms that create these waves that travel
Well,
at the
remember the
surface.
ice going,
Yeah.
Or does the ice do that too?
That would actually dam, I think that could dam some of this.
Yeah.
You'd really want the Arctic to be totally open and subject to huge winds and really.
Yeah. I don't know that exactly, but I know that it's the winds and it's the winter storms that create these big wave heights that generate the most energy.
What happens if you have a very large major event, an earthquake or a tsunami,
So,
you know, huge landslide?
yeah, it's a good question.
It just swamps everything.
It does. So that's why we do this amplitude normalization.
Okay.
So what we try to do is a sliding, say, absolute value or RMS normalization that cuts down those signals from the earthquake. Because you could imagine if you had an earthquake coming from this direction,
Just
it would just kill everything, and
Yeah.
it would just be all artifacts.
Hmm.
So what we try to do when you do this is you normalize the amplitudes, you cross-correlate that time section, and then you actually normalize again the amplitude there before you stack them all together, so that every time window contributes evenly.
Okay.
And then if you do it over enough, it's just the ocean noise that's stationary there every time.
Are there any land-derived noise sources, traffic, or things like
Yes,
that?
so definitely people use this for this exact same principle for geotechnical. So VS30, this, where you characterize the top 30 meters of the shear wave structure. You can just lay out a bunch of 1 Hertz geophones or 4 Hertz geophones, record traffic noise for a day, go and cross-correlate it, and out pops the impulse response between each receiver.
Very
So,
good.
yeah.
All right, well, thank you, Dylan.
Yeah.